Hello. This is video 17. And after all this time, we're finally going to get around to a new data structure. Yay! That's the good news. The bad news, yeah, it's going to require a substantial running start. The why we need to do this and terminology out the wazoo. So before we even dig in and start that ball of wax, let's do a quick aside. A short walk down memory lane for an aside. Let's briefly, quick revisit, Q-U-I-C-K, revisit that old, age-old battle, linked list versus arrays. Remember that? Bounded versus unbounded. They each have their very own advantages and disadvantages and all that sort of stuff. But let's look at it in a particular context, maybe for a particular application. Well, it's not really a particular application. It's a whole collection of applications. Searching, S-E-A-R-C-H-I-N-G. Let's find something that's in there. Or maybe we find out that it's not there. Either way, it could be successful, it could fail. Maybe we'll use Boolean function. That's way ahead of the game. Searching, for example, let's suppose we have an ordered list. We know what that is. It's a linked list where we were just very careful to make sure that everything was put in there in order. Well, we've got an ordered list. In that ordered list, let's find 26. There's nothing magic about 26. This is just a specific example, nothing general about it at all. So we would start searching at the very first node that has any real data in it. Maybe it has a 1. That's not it. We don't know if 26 is in there yet or not. Maybe the next one is a 3. Well, that's not 26 either. And then maybe a 7. I don't know, we could make this up indefinitely. And maybe after the 7, now remember, we're not allowing any duplicates here. That's one of our ground rules for an ordered list. No dupes. No. And yada, yada, yada. And we come in for a landing over here maybe at 24. We're getting close. No, that's not it. And then maybe after 24 is 26. Yay. Ding, 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 ding. Success. Wonderful. How could it have failed? Well, if we had 1, 3, 7, yada, 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 24, and then 27. If we've done a proper job of keeping this in order, when we run into something that's larger than 26, then we know we're not going to find it, and we can return failure at that point. Now, that's not necessarily the end of the list. Maybe after 26, there's 31, and yada, 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 I don't know. Maybe it goes out forever almost, and it ends up at 701. Who knows? We didn't have to look at the whole list. We only have to look at it since we kept it in order. That was a good thing. We kept it in order, so we know we can cut our losses short if we get to a point where 26 should have been and something else is there that's greater. So it's not too bad. In fact, that is what we in the biz would call order, with a big script O here, order in searching, S-E-A-R-C-H-I-N-G. Order in searching. What does order in mean? That means that the number of operations or the number of instructions that have to be executed or the amount of time, whatever it may be that we're measuring, we absolutely always have to choose something that we're measuring. Typically, it's going to be the number of comparisons when we're doing something like sorting or searching. But order in just means it depends on how many things are in the list. So in this case, if there are, say, let's see, up to 701, let's say that there are 600 things total in the list. We would expect the search time to, on average, have to look at about 300 of those. Yikes. If there are 600 things and we choose randomly something that could be in the list, on average, it's going to land about halfway. You know, a lot of times it's going to be before that. A lot of times it's going to be after that. You can see how it would average out to be 1/2 of n. But that's still order in. Why is it called order in? Well, order in actually is a description of how bad we could expect this searching to get as the list gets larger and larger and larger and larger. So if this list that's got lots of dots, waving hands, and so forth, if this has 600 in it, then we could expect, if we double the number of things in the list up to 1,200, we could expect the runtime, the time it takes to find something in the list, to roughly double. That's what it means. It means that the time it takes to do the searching, the number of comparisons it takes to do our searching, is going to be directly proportional to the number of things in the list. So if we double the number of things in the list, twice as long for searching. Oh no, the list increased by a factor of 10. Then we can expect, on average, our searches to take 10 times longer. That's what order n means. Now then, that's only half of the picture. The other half of the picture, maybe, since we want to compete with an ordered list, maybe example 2, we have an ordered array. An array where when we insert things, we keep things in order. Have an ordered array. We haven't implemented any such thing, but that's not too hard to imagine. And let's find 26. So an array, of course, is going to look different. Maybe it's got exactly the same stuff in it. So it's got 1 and 3. I'm not going to draw all the dividing lines, but you know what an array looks like. 1, 2, 7, a bunch of other stuff. 24 and 26 is in there. And 31, then a whole bunch of other stuff. And then way out at the end, the last one that we've got in here is 701. Why did I say it like that? The last one is stored in the array, but maybe we had to accommodate many, many more than that. Aha. One of the disadvantages of the array, since that's bounded, we have to make a prediction, a worst case scenario prediction in advance, and make sure we've got an array large enough to hold however many numbers could be possible in this particular application. So there's one problem. Let's see here. If this is sorted, now we can actually take a shortcut here. If this is sorted, and we're looking for 26, then the first thing to look at actually is not the first element in the array. That's going to be kind of slow. We could do it. Whoops, that's not supposed to be a 2, that's supposed to be a 3. We could do it just like we did this. We could look at this one. No, that's not it. No, that's not it. No, that's not it. Yada, 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 yada. And in this particular case, you know, with 701 as the last one, that might not be too bad. But on the average, we're going to be able to do better than order n. How so? Well, the better place to start looking is not the beginning, not the end, but close to the middle. Close to the middle. So if I said what? There's 600 elements in there. Let's say that this is index 300. And let's say at index 300, dots before, dot after, maybe there's 275. Maybe that's the answer that's sitting there. Is that our 26? No, that's not our 26. Lower. Connection to something here. We go lower than that. And this is not drawn to scale at all. But what we're going to do is we're going to go lower. We'll divide the index in half and look at index 150. Come back way over here somewhere to index 150. And it's still going to be lower than that. And we go, maybe at some point we overshoot and come back this direction. What we're going to do, this picture is horrible, by the way. What we're going to do is jump around. We start halfway through the array. If it's lower, then we cut the index in half, look at 150. If it's more than that, then we cut the difference in index in half again. And what would we be looking at? After 150, 150 divided by 275, 150 is 225? I'm not doing the math very well. But you can see how the index numbers have bounced around, and we're going to zero into it much more quickly here. Good grief, what a horrible example. I hope your imagination is strong enough that you can fill in the blanks in all of that feeble explanation. Start in the middle. Every time. Now, here's the key point. I don't want to sweep this under the rug. What's going to make this faster in the sorted array is that every time we make a decision to either back up and look lower or increase and look higher, we are cutting the search space in half. Let me say that again. Every time we go either lower by half of the indices that we're looking at or higher by half the indices that we're looking at, we're cutting the numbers that we have to look at. The list of numbers we have to look at, we're cutting that in half. So a better way these arrows would be, let me just do the arrows without the array. We go halfway over. Oh, no, it's less than that. Then we come halfway back. Oh, no, it's greater than that. So I go halfway of the remaining indices over. Maybe this picture's better. Oh, it's greater than that. Half again, half again, half again. And eventually, I'm going to zero in on it pretty quickly, even if the list is pretty large. This is going to zero in on what we're looking for much more quickly than in our sorted list, our ordered list. So the moral of the story is arrays win. Let's use arrays and forget about it. Forget about it. Well, we haven't done the order first. Let me switch back to black. That rust is just not satisfactory to me for some reason. Let's say there are 32 elements in the array. Then after we make a decision higher or lower, and we cut off either the top half or the bottom half, then there are 16 elements that are still in our search space. That's what it's called. We're still trying to find 26. Oh no, we cut that in half. Then there are 8 elements left in the search space. How many times can we cut it in half before we've got to find it if it's there? 32 cut in half once is 16. Cut in half again is 8. Cut in half 4. Cut in half 2. Cut in half 1. And if we didn't find it then it's not there. This is how many times you can cut 32 in half. Also known as log base 2 of 32. Logarithms, heard of those? Logarithm is the exponent you have to put on the little number to get the big number. Holy moly. What exponent do I have to put on 2 to get 32? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. 5, which is an alternative way to think of it to the original description I gave. How many times can you cut 32 in half until you can't cut it in half anymore if it's got to be a whole number? Once, twice, 3, 4, 5. Thrice, thrice, fives. Cut it in half 5 times. Log base 2 of 32 is 5. We cut stuff in half in computer science and sorting algorithms and searching algorithms and all that stuff so often that we get our very own notation for logarithm base 2. It's just LG. LG of 32 equals 5. We assume in computer science when you see LG written like that, that means log base 2. For just this reason, cutting the search space in half at each step. Zeroes in on it much more quickly. What's another logarithm? Another example here, 4. Powers of 2, they come out even. The others don't come out even, but it's still going to be approximate. 2, I can cut that in half and get 2, cut that in half and get 1. What's the philosophical implication of that? Well, that means that LG4 equals, think about it, let's see. It's either, I can think of it as the number of times I can cut 4 in half, or it's the exponent I got to put on 2 to get 4. The exponent I put on 2 to get 4 is 2. What's all that black stuff for? Well, with an ordered array, searching is order, drum roll, log in rather than in. And I didn't leave any room for that. I'll put it way down here. Order, log, LG in searches. Put that in a box. That's the one that goes with the sorted array. Put this in a box. That's the one that goes with the linked list. So there is a clear winner here. A sorted array beats the socks off of an ordered linked list if we're going to be using this to do a lot of searches. Think of it this way. If all we're doing up front when we do the initialization, maybe it's even done in the constructor, I don't know. Maybe it reads in an input file and creates the sorted list, the ordered list. Then everything else that's done in the program is just tracking stuff down. Is it in there? Where is it? All that kind of stuff. Then this is going to dominate the behavior of the program, whether we're doing order in searches all the way through or we're doing order log in searches all the way through. If you were to graph those using graph paper, come up, pardon me, a bunch of values of n. I'm just using the board space ridiculously today. I'm sorry about that. But as n increases here, log in looks like that. It's a straight line. Log in, oh, it's much lower. Its growth rate, this is log in. This is in. This is growing at a much slower rate. If n increases, and this is the time it takes to search for something, the time it takes to search for something in this list is going to increase much faster than the time of this one. What do I mean by that? Well, let me see. I was pretending 600 things in the list. Let's double it. If I double it from 600 to 1200, I can expect one additional comparison per search over the 600 list. Yikes. That is a dramatic difference. Why? Because I can cut 1200 in half one more time than I can cut 600 in half. See how weird that works? The log base 2 of n grows really slowly. Actually, this probably should have been closer to this line down here. Even slower than the way I made it look on this graph. So these are much preferable. Much, much, much preferable. Is that all of the aside? Yeah, that's all the aside. End of walk down memory lane. And still no new data structure. You know, this is almost an entire video of walk down memory lane. Let me clear the board. Of the aside, the lengthy aside. My whole world's falling apart here. I think I just unplugged my microphone. Did I? I hope not. I'm not quite done. I don't want to do this whole thing all over again. It's too late, but I should have just shut down the video there where the board was full and say, we shall continue with the next video, but we're already here now, so we'll stay here. I'm going to vent and moan and groan since my life is so horrible right now. It's not really, I'm just saying that to be funny. Dear Santa, what am I going to write to Santa? 2020 has been awful. 2020 is awful. Will you please bring me a data structure that has the best of both worlds? What could that possibly be? That is unbounded. In other words, I'm stingy. I want it all. I want it to be unbounded, like an ordered list. I can put as many things in there as I want. I don't have to know how many there are in advance. I'm not going to worry about running out of memory on the machine. It can start paging to the cloud if it needs to. Okay, will you please bring me a data structure that's unbounded? Well, we got that, the ordered list. But also supports order log base 2 of n searches. Yikes, we just want it all. And that was a question to Santa. Will you please bring me a data structure that is unbounded but also supports order log base 2 of n searches, which means that every time I do a comparison, I cut out half of the number of things that I have to look through to find what I'm looking for. And Santa says, Satan, no, not Satan, Santa, well, maybe Satan. Santa says, here, have a tree. A tree grows in Brooklyn. And we think, well, we didn't want any little fledgling house plant to put in the backyard or anything. It turns out that a tree is a data structure that we're going to be looking at for quite a while, maybe the rest of our lives. A tree is a data structure that, first of all, is unbounded, and second of all, definitely does have order log n searches. And it's a professional level data structure, even more so than the linked list. For starters, this was for starters. For following up on starters, there's a lot of terminology we got to discuss before we can get into the real stuff about trees. So the next video is going to be introduction to terminology, almost like a dictionary. See you online.